This is the third lesson of our topic Trigonometry 3 from 4 KCSE syllabus. And in this lesson, we will look at some transformations that happens to a trigonometric wave when we make some changes to a function. For example, we have y is equals to sine x. What happens if we multiply this function by 3 such that we have y is equals to sine x? So in this case, we look at what happens to the amplitude and the period, which we have covered in lesson 2. So let's plot two graphs, compare them, analyze them, and see what has happened. Find out whether we can have a description of the two waves in comparison, that is, in terms of transformation. So we are going to plot the graphs of these two functions, that is y is equals sine x and y is equals to 3 sine x, and see what happens when we compare the two. So let's fill our table here. We'll start with the values of x. So here we start with 0. We have 30, 60 degrees, 90, 120, 150. This is 180. We have 210. We have 240. We have 270. We have 300. We have 330. We have 360, we have 390, we have 420, we have 450, 480, then we have 510, we have 540, we have 570, we have 600, we have 630, 660, 690, and finally we have 720 degrees. From there, we fill the values of y is equals to sine x, and here when x is 0, you say it is this is 0, this is 0.50, this is 0.87, this is 1, and we have 0.87, we have 0.50, we have 180 is 0, and then we have minus 0.50 minus 0.87, and we have minus 1, then we have minus 0.87, we have minus 0.50, then we have this is 0, we have 0.50, 0.87, 450, 450 we have 450 is 1, it is 1, so we have this is 1, we have 480, it is 0.87, then we have 510, it is 0.50, then we have 0 minus 0.50 minus 0.87, we have minus 1 minus 0.87, then we have 690 is minus 0.5 minus 0.5, and we have 720, we get 0. So these are the values of y is equals to sine x. Now we go to y is equals to 3 sine x. So this means simply means we multiply this by 3. This is 0. 0.50 times 3 is 1.50. Then this other one will be 8 times 8 times 0.87 times 3, you get it is minus 2.61, not minus but positive. That is 2.61. Then we multiply 1 by 3, you get 3. Here you get 2.61. Then you get 1.50. We have 0 minus 1.50. This is minus 2.61. This is minus 3 minus 2.61. Then minus 1.50. Then this is 0. This is 1.50. This is 2.61. This is 3. This is 2.61. This is 1.50. This is 0. This is 0. This is minus 1.50. This is minus 2.61. This is minus 3 minus 2.61 minus 1.50, and this is 0. So we are going to use this table to plot the graph or waves of y is equal sin x, y is equals to 3 sin x. We compare the two and see what happens. Can we be able to describe one wave in comparison of the other? So we are going to plot the graph of these two functions. So let's start by labeling our graph. So this is the starting point. You can say this is 1, this is 2, and this is 3. This is our y-axis. So we have minus 1, minus 2, minus 3. Then the x-axis, we have, let's use, we have 90 degrees. We have 180 degrees. We have 270. We have 360. We have 450 degrees. So here we have 540. Then we have 630. We have from there we have 720. So this is our x-axis. Now, using on the same Cartesian plane, let's identify the points that we use to plot our graph. So we are going to start with y is equal sin x. So 0 we have 0. Then 30 is here, we have 0.5. Should be. So from there we fill our point, or identify our point for y is equal sin x. So when x is 0, we have it is 0. I'll use 90 for convenience. So when 90 is 1, we have 1. When then I go to 180, which is 0. Then I'll go to 270, which is minus 1. Then we have 270. We have 360. 360, it is 0. Then we have 450. It is 1. So 450, we get 1. Then 540, we got 0. Then we have 630 is minus 1. Then we have 720, we have it is equals to 0. So when we join these points, we should be able to come up with a graph that or the wave of y is equals to sin x. So this is our graph of y is equals to sin x. From there, we go ahead and identify the points of the other graph. that is y is equals 3 sine x. So we start also from 0. We start from 0, so we have this is our point. Then from there 90 we go to 3, so here we have 3. Then we have 180, it is 0. Then we have 270 is minus 3. Then we have 360. 360 is 0. Then 450 we get to 3. Then 540 we get 540 we get it is 0. Then we get 630 is minus 3. That's where our point is. And 720 we have 720. We join this point to come up with a graph. So this is the graph of our function y is equals to 3, that is y is equals to 3 sine x, and therefore we can compare these two. You find that for the first one, the amplitude, the first graph of y, for y is equals to sine x, amplitude is equals to 1 and period is equals to 360 degrees. So this is 1. For y is equals to 3 sine x, we find that amplitude is equals to 3 and the period is the same as above, 360. So if you look at the three graphs, there is a transformation such that for you to get this graph, y is equals 3x from y is equals to x, it's like you multiply the period by 3. So the period of the two waves is 360 or 2 pi. So we can conclude by saying the amplitude of y is equals sine x is 1, while amplitude of y is equals sine 3x is 3. The period of both function is 360, not 1. It is 360. So we can say that when we change the constant, the amplitude, that is amplitude increases or decreases with the same magnitude in terms of transformation. Y is equals 3 sine x is obtained by stretch of factor 3 and y-axis invariant. So we are going to plot two more functions, that is for y is equals to cos x and y is equals cos a half x. So note here, we have not multiplied, but we have divided the angle by 2, that is a half, and you plot within the range of 0 to 810, then we observe what happens. So I'm going to fill my table and plot the two functions. So this is my table. I have already filled in the values that I'll need. So I'm going to use this table to plot the graph of the two functions y is equals to cos x and y is equals to cos a half x and see what happens. So I have plotted the two graphs. That is a graph of y is equals to cos x and y is equals to a half x. So you can see that the two graphs are different, but we can relate them. You can say that you can get the function of y is equals cos a half x by stretching y is equals to cos x, stretch factor 2 with yx. So stretch factor 2, y-axis invariant. So invariant And this means that you can see the period of that is y is equals to cos x. The period is or the amplitude is equals to 1, and the period is equals to 360 degrees. For the other one, y is equals to cos a half x. The amplitude is the same, that is 1, but period changes to 720, that is to make a complete cycle. So you find that we can make a conclusion that when we reduce x by a half, that is the angle, the period doubles. Then you can ask yourself, what happens if we would multiply the angle by a certain constant? What will be the changes of the period and the amplitude? So in conclusion, then we can say that when the period of y is equals to x is 360, and while the period of y is equals to cos a half x is 720, we can describe this transformation. Y is equals to cos a half x can be obtained by a stretch of factor 2 with the y-axis invariant. So note, when the angle is reduced by a half, the period doubles. What would be the period if, for example, we say y is equals to cos a third x? What will be the period when you compare it to y is equals to cos x? You can plot and see what happens. So let's take another example. We draw on the same axis the graph of y is equals cos x and y is equals to 2 cos a half x. State the amplitude and the period of each wave. So I'll go ahead and make a table for this two functions so that I can plot them. I have prepared the table that I will need to plot the two graphs. So I have the values of x, the values of y is equals cos x, and the values of y is equals 2 cos a half x. So let's plot the two graphs and see what happens. These are the two graphs of the two functions. Y is equals cos x and y is equals to 2 cos a half x. So we notice that for y is equals to cos x, the amplitude is equals to 1, and the period is equals to 360 degrees. That is from there up to here. Then for y is equals to that is 2 cos a half x. The amplitude is equals to 2, that is from 0 to where we have 2, and the period is equals to 720. So clearly we can see that when we multiply our function by a certain constant, the amplitude increases by that margin, and when we divide the angle by a certain figure, a constant, then the period is multiplied by the same number. So we can see a trend here. So let's plot the graph of y is equals to sine x and y is equals to sine into bracket x plus 45 degrees and see what happens. So I'll go ahead and make a table for this graph, then we plot. This is a table that I'm going to use to plot the graph of these functions. So I'll start with x. X I'll start it from 0. So we say this is 0. We go to 45. We go to 90. Then we have 135. For the other one is 180. Then we have 225. We have 270, and then we have 315, we have 360, then 405, we have 495, then we have 540, we have 585, and we have 630. So we go up to that. Then we have the other values. So this angle here now, we'll add the angle up here, we add 45. So 0 plus 45, you get 45. This you get plus 45 is 90. Then we have that 135. We have 180. We have 225. Then we have 270. We have 315. We have 360. We have 405. We have 495. We have 540. We have 585. We have 630. And when you add 45, you get 675. So we now fill the values of y is equals to sine x. So here we have 0. We have 0.71. We have 1. We have 0.71. We have 0. We have minus 0.71. We have minus 1, minus 0.71. Here we have 0. We have 0.17. Then we have 1. We have 0.71. Then we have 0. We have negative 0.71. And we have minus 1. So that is, those are the values of, then for y is equals to sine x plus 45, we are going to fill these values. So here we have 0.71, we have 1.00, we have 0.71, we have 0, we have minus 0.71, then we have minus 1, minus 0.71, we have 0, then we have 0.71, then we have 1, we have 0.71, then we have 0, we have minus 0.71, then we have minus 1, then we have minus 0.71. This is 0.71, not 17. So we now have the values. So what remains is to use our values to fill the table to come up with the graphs. These are the graphs that I have come up with. This is a graph of y is equals to sine x. And this is a graph of y is equals to sine x 40 plus 45 degrees. Now, if you look at this graph, you can see that the amplitude is the same. Amplitude is equals to 1. Period is the same. It is 360. But we can see that the graph of y is equals to sine x plus 45 kind of leads the other, and a difference of 45 degrees. So to describe this transformation, we say that y is equals to sine x plus 45 can be obtained from y is equals to sine x by a transformation of that is of minus 45 and 0. And the angle difference is 45. We refer to that angle as the face angle. This is the face angle. Maybe we can put it clearly. So we can conclude by saying that the amplitude and the period are the same, i.e. 1 and 360 degrees. The transformation y is equals to sine x plus 45 can be obtained from y is equals to sine x by a translation of minus, this is a translation vector, minus 45, 0. The angle difference of 45 is referred to as the face angle. So that is how you do that, and that brings us to the conclusion. So from here, we are going to analyze the 3 graphs that we have plotted so that we can make some conclusions. So we can put our formula in general and say if y is equals to k sine bx plus or minus theta, or y is equals to k cos bx plus or minus theta, where k, theta and b are constant, then we can say that the amplitude of the wave is k. This is our k here, and this is our k. That is the amplitude. The period of the wave is 360 degrees divided by b. This is our b here, or 2 pi radians divided by b. Then finally, the angle theta over b, this is our theta, you divide by b here, is a face angle. So it is important that you note that, so that whenever you are given a function, even without drawing, you can determine the amplitude, the period, and the face angle. And that brings us to the end of this lesson. You are all welcome to our 4th lesson and the last one in this topic. So you are all welcome.